Welcome, AP Physics students. You have completed, hopefully, free response practice 2. And once again, I'm going to walk through myself solving these problems, including saying some tips and tricks that I think might be helpful. I'm going to keep an eye on the clock, and we'll see how the timing goes. Okay, so let me get my timer ready. We're going to do question number 1. That's the qualitative quantitative question. So that's the one that should take us about 25 minutes. Okay, here I go. Starting my timer. Let's read. Starting off with question 1. Okay, let's see. 25 minutes suggested. I have this diagram right here. The disk shown above spins about the axle at its center. Okay. A student's experiments reveal that while the disk is spinning, friction between the axle and disk exerts a constant torque on the disk. Okay, the disk above spins about the axle at its center. A student's experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque. So this is maybe a little different than the problems we normally see. There is, in fact, friction between the spinning object, and they say that that friction is applying a constant torque. Makes me probably think that frictional torque, that frictional force is constant as well. Therefore, maybe keep that into account. We can't assume there's no friction because they're telling us otherwise. Okay, there's this scenario. A. At time t equals 0, the disk has an initial counterclockwise, which they're telling us is positive, angular velocity omega naught. So when the clock is starting at t equals 0, it's already spinning in the positive counterclockwise direction with the speed of omega naught. The disk later comes to rest. Ooh, okay, it's stopping at t equals t1. Oh, weird annotation. I. On the grid at left below, sketch a graph that would represent the disk's angular velocity as a function of time, t from t equals 0 until the disk comes to rest at t equals t1. Okay, so this graph here on the left, angular velocity. So the angular velocity of the disk starting at 0 over time. Ooh, and I end at t1. And what was t1? T1 is when the disk comes to rest. And it starts with an angular velocity of omega naught. So I have angular velocity here. Look right here. They've labeled omega naught. And it says that's the speed of the disk when it starts off. So it's starting the line, whatever the line's going to look like, it's starting off right like this. Okay. Now let's think what's happening with this disk. It's spinning. Normally, like Newton's first law, an object in motion stays in motion. Normally, it would just be constantly spinning. But it says there's a constant frictional torque. Let's double check. There's spinning friction between the axle and the disk exerts a constant torque. Okay, I know it doesn't ask to prove it, but I know that if there's a torque, that causes an acceleration. And if there's a frictional torque, that's going to cause a deceleration, right? A slowing down. Well, if the torque is constant, that acceleration should be constant. I should have a constant slowing down, a constant negative or opposite acceleration. So let's see, this is a velocity versus time graph. Acceleration is the slope. So if I want a constant acceleration, I want a constant slope that's negative. And then let's see, at t1, that's when it's at rest. So I should have 0 angular speed at t1. I should have a straight line, and let's see if I can do this on my PowerPoint. Ooh, something like that. This is a straight line. Probably don't have to write a straight line as long as it's clear you're trying to make it be a straight line. Okay, straight line like that. 2. On the grid at the right, sketch the disk's angular acceleration as a function of time from t equals 0 until the disk comes to rest. Well, okay, this is angular acceleration. I know that if I have a velocity graph, the slope of the velocity graph is the acceleration. Here I have a constant negative slope. I should have a constant negative value. And again, that should make sense because we saw that the torque from friction is constant, so the acceleration is constant. And this is a frictional torque, which is usually opposing, or it is opposing sliding motion. So I should have a negative acceleration. All of these are just asking to sketch. So I'm not plotting anything, but I should have some constant negative. Maybe I'll draw it right here. I know my little webcam's in the way. So a constant negative. This should be a flat horizontal line. If you drew it here, that should be okay. If you drew it down here, that should be okay. What they would care about is a constant negative horizontal line. A horizontal line below the x-axis. Okay. All right. Well, maybe I'll double check if I have time later, but let's keep going. B. The magnitude of the frictional torque exerted on the disk is tau naught. Derive, I'm doing some algebra. Derive an equation for the rotational inertia I of the disk in terms of tau naught, omega naught, and T1, and physical constants. That's like G. Now, T1 and omega naught. Let's remind ourselves. Let's see. What was T1? Oh, T1 is when it comes to rest, and omega naught was that initial velocity. That's right. Okay. So this here was the initial velocity, and that makes sense, omega naught. And T1 was when it comes to rest. So I'm trying to derive an equation. I have torque, I have velocity, and I have time. There's probably several ways to solve this problem. If I have torque, velocity, and time, can I think of an equation that relates those? I know like the impulse equation says F times T equals delta P or delta mv. Now that's for linear stuff. I know that tau times time is equal to, well, let's see, the change in angular momentum, like this. And this is good because I'm trying to find the rotational inertia. So look at this equation. I know the torque, it was constant, so that would be tau naught. This is the torque from friction, right? There's only one torque acting on that disk once it's spinning. That's friction. So this is the frictional torque. T is going to be the time for it to be moving and slow to a stop. And this is the change in angular momentum. So let's see, tau naught multiplied by T1 is going to equal, well, that would be, of course, delta I omega, that would be I omega minus I omega naught. Okay, so I omega minus I omega naught, where this is the starting speed. Let me cross this off so graders don't get confused. Okay, so this is the starting speed. Now, T1, remember, that's when it's coming to a stop. That's when it's coming to a stop. So what's the final velocity when it's coming to a stop? The final velocity would be equal to 0. So that's going to end up canceling out. Okay, so then I have, where'd my pen go? I have tau naught times T1 is equal to minus I omega naught. So if I solve for I could divide both sides by this minus. So I have tau naught times T1 divided by omega naught. And there should be that minus sign, something like that. Oh, I don't know about that minus sign, yuck. Okay, but yeah, there's me using the impulse equation. Okay, I think that's pretty good. Let me pause right now. I'm going to keep my timer running, but you could have used like a constant acceleration equation, right? You could use that in combination with Newton's second law, because you know that tau is equal to I alpha. And then if you use one of our acceleration equations and plug in this for acceleration, you could probably get the same answer. Maybe you could use the work energy theorem. But to do that, remember for work energy theorem, that's tau times delta theta equals the change in kinetic energy. That might be a little rougher, and you'd have to find that distance. And they don't really want distance in that equation. So maybe it's possible, but that might take a little bit longer. Okay, try and use these terms that they have here. Okay, back to it. Let's see my clock. Okay, I got 9 minutes and 50 seconds, just about 10 minutes Remember, I have 25 minutes for this problem, so I'm going to keep going. Keep going. C, in another experiment, the disk again has an initial positive angular velocity at time t equals 0. At time t equals 1/2 t. Oh, yeah, God, what is this? What was t1? What was t1? They said t1 was when it comes to a rest. Okay, t1 was when it comes to rest. All right. So when at half the time until it stops, the student starts dripping oil, oh my goodness, on the contact surface between the axle and the disc to reduce the friction. As time passes, more and more oil reaches the contact surface, reducing the friction even further. Boy, this seems really complicated. Mr. Thrasher hasn't really talked to us about like oil before. Well, I mean, maybe it's a weird scenario, but what's it really saying from the physics that I know? It says that it's reducing friction. Okay, so the weird oil thing, what's happening is the friction, the torque, or the force, but we probably care about the torque is going down as we're adding that oil. So starting at this weird half time, the torque is going down. Okay, on the grid at left below, sketch a graph that could represent the disk's angular velocity, oh, that's similar to what we did before, as a function of time from t equals 0 to t equals t1. And isn't that the same time as before? Oh yeah, 0 to t1, which is the time for the disk came at rest in part A. Okay, nice. Okay, so I'm making another velocity graph. This is seeming really similar, except that I start dripping oil. Now, am I dripping oil from the beginning? At time t equals half t, the student starts dripping oil. Okay, this is important. I'm not dripping that oil until half t. So the first half of this motion, the first half of the time, the disk was spinning like it was before, where there is friction. So again, it's starting at some velocity omega naught, and then as it's spinning, it's slowing down. It's not coming to rest. I probably shouldn't go to here because it seems like they're starting to drip oil while it's still spinning. But for a little bit, I have this line going down, and it should be straight. Oh man, Mr. Thrasher, this is a product of bad drawing ability on my graphics tablet. But I should have a straight line because in this first half, there's no oil being dripped. So again, that torque is constant, and that means the acceleration, the deceleration is constant. But then at t equals 1/2, what did we say? The torque is decreasing. So if tau is getting smaller, the disk has the same inertia. Well, let's see, the acceleration must be getting smaller, that deceleration. That deceleration must approach 0. Now, okay, and this is a velocity graph, so the slope is the acceleration. If the acceleration is approaching 0, then the slope should be approaching 0. So I'm going like this, right? Here's my initial slope. I could keep going, but it should approach 0 until, ooh, wait a minute, Does it say it stops at t1 again? Because if it stops at t1, oops, what's happening? If it stops at t1, oh gosh, come on, document. If it stops, hold on, I'm going to pause. Okay, sorry. Sorry, I had to pause because I was having some technical difficulties. Now, if it's stopping at t1, oh man, I should still probably get back to 0 here, but I need that changing slope. It needs to curve like this. So it should be curving. Maybe, if I made my line steeper and it curving like that. So it should definitely be curving in this second part. If I have time left, I'll clean this up a little bit. Let's go on though to part 2, the acceleration. Again, the first half should be that same acceleration, the same negative acceleration as before. But now I start dripping oil. So there's less and less friction. So the amount of acceleration should go down. It should approach zero. So then maybe I have something that's approaching zero, something like this. Boy, should I have it curved? It doesn't really say like the rate the friction is going down. Yeah, boy. I mean, normally I would just make a line going towards zero, right? The acceleration is decreasing or it's approaching zero. So I'm not sure if I should do this or if I should curve it somehow. The problem's not really clear. Maybe they'll give a point for something like this, at least if it's close. But let's keep going. If I have time, maybe I'll come back to that. I definitely know that this acceleration should go towards zero. I'm just not sure if it's like this, or maybe it's like this, or maybe it's like this. Maybe they'll assign points to that, but I'm not sure yet. Let's keep on going. Okay, D. The student is trying to mathematically model the magnitude of tau, of the torque exerted by the axle on the disc when the oil is present at a time tau greater than half, or t greater than 1/2 t1. Boy, God, they use confusing notation, but they're just saying here, when the oil is present, they started dripping the oil after that half time, right? So half the time the disc is spinning no oil, then they start dripping oil. That's all it's saying right here. Okay, sometimes they might use confusing seeming notation, but the scenario is probably just carrying over. The student writes down the following two equations, each of which includes a positive constant, C1 and C2, with appropriate units. I'm going to keep my clock running, but here's a tip. If they're giving you constants, usually you can ignore those constants. They're not going to be part of the answer. They're doing that to make sure their equation could still make physics sense. And I'll say why in a second. Okay, so they give me these two equations. Okay, yuck. Which equation is a better mathematical model for this experiment? One or two, and briefly explain. Okay, well, let's look at this equation. For number one, I have tau. That's the torque from friction. I have this constant. I'm kind of going to ignore that constant. And then I have t. T is how long the thing is spinning, minus half. Boy, this is a confusing looking thing. This is also kind of confusing, but at least it's the same for both of these, right? So one of these can't be more correct or another because of this, because this looks identical. But this is confusing, but it's clearly having something to do with time, right? It clearly has to do with the time that's passing. So this equation is saying there's torque is related to the constant multiplied by time. And I'm going to jut in again, right? They have this constant here because obviously torque isn't equal to time, right? These are very different physics things. So they're including this constant. So like you could still have something, you know, maybe this is in units of Newton meter, per second things, so it could still keep this equation physically valid. But again, you can mostly ignore it. So here's what I know about this equation. It has time and torque. And where this time is located, if the time increases, the torque increases. If I have more and more time, I know I'm subtracting something, but still, if I have more and more time, the torque is going up. Does that make sense in this scenario? As time is passing, is there more torque? No, the torque is decreasing. This is a weird equation. I've never seen it before. Thrasher never taught it to me, that jerk. But what it's saying is that when time is increasing, the torque is increasing. And that doesn't match the scenario. It's saying the torque is going down because I'm dripping more and more oil. I'm reducing the friction. I don't know about one. Let's look at two. All right, now I have C2. And then in the denominator, I have a time. So if time is increasing, if this is in the denominator, the result would have the torque decreasing. Does that make sense? Yes, it does. Because again, we're dripping oil. We're removing friction. So, okay, so what am I going to write down? Let's see. More time means more oil, so frictional torque decreases. That's what should be happening. Okay, equation 2 shows that as time increases, the torque decreases, which matches. There's my 2 sentences. Sorry, you might cut off my word with this thing. Matches. Oh gosh, let me go like this. Matches. Technological difficulties. Okay, I got 2 sentences. To be honest, that means I've covered this. If I have more time, maybe I'll explain why equation 1 doesn't work. They just say why I selected the plausible one. But again, I'll check the clock, and if there's more time, maybe I'll add on. Equation 1 doesn't work because. Also, maybe I'll try and figure out this graph. Maybe I'll just decide one of these. Maybe I have to take a guess. But at least it should be approaching 0. Let me take a look at how my time is doing. Remember, I have 25 minutes and I have 21 minutes. Okay, so I still have 4 minutes to spare. Notice, though, I hit my big ideas. Okay, notice that I also wrote my answers first. I didn't lock myself into choosing one of these in the beginning. I thought of physics. I even wrote out my answer. And maybe if you're writing out, if something's like, oh wait, well that doesn't make sense, maybe it'll choose your or alter your reasoning. Okay, for this graph problem, I don't believe in actuality they assigned a point for whether it's curved one way or the other. Their solutions has this straight line on it. Okay, but if you're unsure, again, we're trying to get half the points. So there's definitely some things you know. It should be constant like this in the beginning. Maybe that's worth a point. It should definitely be approaching that x-axis, right? One way or another. So you can still make best guesses and probably get at least half of those points. And again, notice I've been reading the problems. If I kind of forgot something, I went back and tried to find out what that T1 was equal to. And I still had time to do that. Even now, as I'm giving kind of a post-mortem, as I'm talking about the problem, notice I still have about 2.5 minutes to still be solving. So you have time to read the problem, reread the problem, give an answer a try. All right, maybe put down your 2 sentences, all right, and then move on. And of course, I know you're not going to be making a graph for this AP problem, but maybe instead of this problem, you were given these 2 graphs, or you were given these graphs. And the question is, do these graphs match the scenario? Yes or no? You would write down yes, because in the first half, it has a constant deceleration, so the slope would be constant, So I know that you're not making a graph on this year's test, but hopefully this is good practice on thinking what the graphs should look like, because you might have to be analyzing them. Okay, that's the end for free response problem number 1 for practice 2. Thanks for watching.